Assalamu alaikum. Hello. Hello. This class is for fabrication and processing. If anyone not for fabrication and processing, you don't have to attend this class. Hello, anyone can respond whether you hear me or not? Hello? Hassan, do you hear me? Hello? Unmute করে একটু রেসপন্স করো।
হ্যালো, আসসালামু আলাইকুম।
ওয়ালাইকুম আসসালাম। হাসান না কে এটা? প্রীতম। প্রীতম শোনা যাচ্ছে?
জি জি স্যার, ক্লিয়ারলি শোনা যাচ্ছে।
Okay, good. So we have very few participants today. I don't know why.
স্যার আরো মেম্বার আসবে
আসবে না? Okay, so let's wait for some time, huh?
জি স্যার, 10 মিনিট ওয়েট করলে আরো মেম্বার অ্যাড হবে।
How do you feel class with Google Classroom?
স্যার গুগল ক্লাসরুমে স্যার মোটামুটি ক্লিয়ার ভয়েস এবং দেখতে পাচ্ছি। ইটস ওকে স্যার।
Okay, good. আমি তো আসলে আপলোড করে দিয়েছিলাম একটা ক্লাস। So what you need to do, you have to go through this class, and mainly you will be doing the self-studying actually. আমি একটুখানি খালি টাচ করে যাব, so you will remember some of my explanation, and then you just go through the materials. The materials is self-explanatory, so you don't have to go anywhere else.
শিওর স্যার।
তোমরা আছো ভালো না?
স্যার ভালো বলতে আমি আলহামদুলিল্লাহ আছি, বাট আমি স্যার মিরপুর এরিয়াতে থাকি, তো আশেপাশের অবস্থা স্যার খুবই খারাপ।
ওহো, আল্লাহ save us all.
Yes, sir.
তোমাদের সি সেকশন বি সেকশনের ছেলেদের সাথে যোগাযোগ হয়েছে? হ্যাঁ বলো। সি সেকশন আর বি সেকশনের ছেলেরা আমি জানি না খবর পাইছি কিনা, সো তোমরা একটু ইনফর্ম করে দিও প্রত্যেক দিন, আর প্রত্যেক দিন না, এভরি টিউজডে মঙ্গলবারে 11:20 ইনশাল্লাহ একটা করে সপ্তাহে ক্লাস নেব, অল অফ ইউ টুগেদার, অল দ্য সেকশনস টুগেদার। তো আমরা তাহলে একসাথে ক্লাসটা শুনলে তাহলে ভালো হবে, everybody will hear the same stuff, and in future when we will open the university, probably we will go these materials again very quickly. Maybe I will ask about any question do you have or anything like that, and then I will go through those confusions and try to solve those things. But this class is the kind of a final class. So what you hear, you just remember and then just go through to the material. And this is for the whole week's class. The next week we will discuss another topic. So if you could contact B and C section to attend the class, so it will be better. And the whole class, after I finish the class, probably we will have the recording in it, and then I don't know yet how to upload it, but I will do the upload also. So anybody who misses it, he or she can go through that uploaded version. So far we have 10 of us, right? We need more students. তোমরা কি মেইলটা পাইতে দেরি হয়ে গেছে নাকি না?
স্যার আমি অ্যাকচুয়ালি মেইলটা পাইনি স্যার, আমার মেইল অ্যাড্রেস দেওয়া হয়নি।
তো আমার মেইল অ্যাড্রেস জানা আছে তোমাদের কাছে?
আচ্ছা স্যার।
তো সম্ভব হইলে তোমরা যারা পাও নাই তারা পরস্পরকে মেইল করে পাঠিয়ে দিতে পারো, বিকজ ইনফরমেশনটা ইউ নিড দ্য মিটিং আইডি নাম্বার and when the meeting is going to start. আর ওই যে আপলোড করে দিয়েছে যে ক্লাস নোটটা, to access in that you need a code number. So that code number also I mailed it to the students. So if you just get it from them, you can have it from them, or you just mail it to my address. I will send it to you. আর ওই একবার পাইলে আর you don't have to get the mail again and again. আল্লাহ যদি বাঁচায় রাখে আর ইলেকট্রিসিটির যদি কোনো প্রবলেম না হয়, or any other problem যদি না হয়, ইনশাল্লাহ every Tuesday মঙ্গলবার 11:20 will meet inshallah, as long as the university is not opening. যতদিন অনলাইন ক্লাস করব ততদিন আমরা ওই প্রতি মঙ্গলবার 11:20। So it's almost 10 minutes gone. So let's start, right?
Yes, sir.
So today we are going to discuss about one of the process we use in the fabrication process for VLSI. That one is called epitaxy. The epitaxy is a single layer or few layer crystal structure. So on top of the wafer, we usually make that layer, and this layer we call epi layer. And if the epitaxy is homo epitaxy, then the same material the wafer is, we'll make the layer in the same materials, not with the different materials. If the wafer is with the silicon, then the epitaxy layer will be made out of silicon. A heteroepitaxy is like a different layers, different materials. So usually the optoelectronics, they use this heteroepitaxy materials or process. Production method, there are 3 kind of production method. One is MBE, that means molecular beam epitaxy. VP, vapor phase epitaxy. LP, liquid phase epitaxy. Actually, this vapor, liquid, these are the phase of the source material. If the source material is from the vapor, then we call it vapor phase epitaxy. If the source material is from liquid, then it's liquid phase epitaxy. If it is solid, then it's called molecular beam epitaxy. And then we'll go through the process of all these three types, LP, MB, VP. And finally, we'll discuss about the defects. When we get the epi layer, what type of defects we might have. We'll go through those. Two types of defects. One is like pattern shifting, pattern and the pattern center gets shifted. Another is faceting or non-planarity. That means the surface gets non-planar. So first here I explain what is epitaxy. Growth of a single crystal film. Film means the single layer or two crystal layer is called film on top of the crystalline structure. This film technology is crucial for VLSI technology. AP means upon, taxi means ordered. That means that the AP layer is a more precise oriented crystal layer. If the wafer or the body is not like well oriented, but the particular layer or particular couple of layer will be highly ordered oriented. So the homoepitaxy is a film and the substrate are the same material. The substrate, if it is silicon, the layer also is silicon. Silicon on silicon growth is called homoepitaxy. Film layer are purer than the substrate. It's really clean crystal structure. Film can be doped individually, independently. This EP layer, not only a silicon layer, it could be a doped silicon layer. Maybe N-type or P-type, we can do that also. That's called homoepitaxy. Heteroepitaxy is film and the substrates are different material, like aluminum arsenide on gallium arsenide growth. Usually the optoelectronics structure use these things. Now we go through the LP, liquid phase epitaxy. If you guys have any question, just knock me, okay? So the LP, obviously the LP, the source material is liquid, and the structure it will grow is solid. So what happened? The substrate and whatever the substrate material is, on top of it we put the solution of the same material. So that solution we kept as a supersaturated melt. So as soon as we just cool down, then the crystal get crystalline, solidify, and then it make the layer on top of the substrate. So temperature is increased until the phase transition occurs. That means until it got supersaturated, the temperature is increased. And when the supersaturation condition is occur, then we reduce the temperature. Then because of this reduction of the temperature, the precipitation of crystals appear on top of the substrate. Large growth can be controlled by controlling cooling rate. Cooling rate, the way we reduce the temperature, depending on that, we can make the layer thickness higher or lower. Cooling could be done in two ways. One is a continuous reduction, another is step reduction. If you want to make a more controlled composition and then proper thickness and then lower defects film, then we do use a step reduction. So the step reduction, when we reduce the temperature for some time and then we stop it, again we reduce the sometime and then we stop it. This way we do the step reduction. So when the reduction is done, so it will crystallize layer by layer, and then we will have a smoother and then the lower defects film. And this advantage is liquid crystal is the surface is more of rough. It is not smooth, and poor thickness, uniformity. So the thickness is not like uniform. So the LP, we can make the thickness better by controlling the temperature, but most of the time we have the poor thickness, uniformity. So the structure of the process is like this. This out big box, this one is called crucible. It's a graphite crucible, and then in the graphite crucible there are few openings, and in these openings we if all of you please go into mute. So you please mute your microphone so that there will be no noise. So the block is called crucible, graphite crucible. In the block there are a few hole, or the where we keep the source material, the film melt, which is supersaturated melt. And within this crucible there is a sliding roll, a slider. That's also made of graphite. And then we gradually pull that slide from left to right, and in that slide there are some slot, and in that slot we keep the wafer. So that we keep, there are many slots inside here also. So the rate we pull it, and the rate we change the temperature. By doing that, we can get the epitaxy layer on top of the wafer. So this is the simple picture of the LP process. Then we will discuss about the MB. MB, here we use the pure material, and then just the way we make the wall of a building. So we just put the crystals on top of the substrate. So that it makes a layer. So the environment is highly controlled. It's an ultra high vacuum UHV system. One or more evaporated beams of the atom yield a film. So this evaporated beam, this comes from the effusion cell. In the bottom you will see the effusion cell is the source of the beam material. So the beam materials, the materials which I want to make the crystal layer or the epi layer, we keep it in the hotted place. It's called effusion cell. So it stay in a liquid condition, and then it forces the materials on top of the wafer. So the surface diffusion. So when a materials get into the substrate, that because of the environment, that goes as a diffusion, it goes inside. So what we do, we prevent the diffusion of those materials in the substrate. So to do that, we control by the temperature. Here it says semiconductor and dopant sources are arranged around the substrate. Each source and the substrate can be individually heated. Shutter controls the exposure of each species, and each effusion cell can keep different materials. Some can take silicon, some can take the dopant. Source can be shield or gas, solid or gas. So solid, if it is solid, then because of heating temperature, it will become like liquid. Or instead of solid, we can take the source as a gaseous form. And there is no chemical reaction with the substrate because those crystals just lay on top of the substrate. It does not make any reaction with the wafer. And then wafer mount on the heated block, and the block rotates in a slow RPM, and each efficient cell has shutter to control the flow of the source material. And in situ cleaning done before the process starts. So before we start to put the materials, before that we clean the wafer inside that process, inside that system. So that the system looks like here. The picture is not that clear. Here is the heated block, and this heated block we place the wafer. This one in the bottom one is the wafer, and then this is the whole thing is in a round vacuum chamber, and there is opening in the vacuum chamber with the shutter. So the shutter controls the materials to be sent on top of the wafer. So it's this is called effusion cell. The effusion cells are the source material. It could be silicon or it could be dopant. Here is a dopant A, dopant B, and then there is a push button or the piston which force the materials to go out, and then the shutter controls, and then it goes on top of the wafer, and then the as many layers we need, we keep it on top of the wafer. So this is MB, and the third type of process is called VP. In the VP, first we flow hot hydrogen gas to clean the or bring the temperature equilibrium. So the furnace get everywhere almost the same temperature. Then we send hydrochloric acid gas to clean the wafer. It is kept for 3 minutes, 1150 to 1200 degrees Celsius. So the wafer get clean. After that, the volatile compound, both silicon and the dopant, flow towards the substrate. Then we force a gaseous form of materials to the substrate. And then that gaseous material react with the substrate to form a element, our desired element, which we want to make the epi-layer, and then it gets the component for the epi-layer. And the source material usually is silicon tetrachloride plus dopant. Silicon tetrachloride plus dopant. So the silicon dichloride forms silicon and silicon tetrachloride, and silicon tetrachloride react with hydrogen and then make the silicon and hydrochloric acid. The hydrochloric acid byproduct we get it out, and these silicons, pure silicons with a particular orientation, which stay on top of the substrate. And the furnace or the reactor we use in this process is 3 types reactor. We call the furnace as a reactor. There are 3 type reactors. One is horizontal type, another is vertical type, another is barrel type. This one is barrel type. The horizontal type, the furnace is horizontally laid down, and then there is a tilted holder for the wafer. And these small blocks, these are the wafer or the substrate. And then from the left side, we gas chemical source. We send it from the left side, and then around it is a heating coil, and then we need the particular heating temperature, and then this gas goes through the wafer and then get out from the vent. So when it touch the wafer, so it creates the epilayer of silicon. So in this, we get the, it's the low cost, but not uniform deposition. So since it is tilted, so the deposition is not vertically done. It is kind of tilted condition. So that's why the epilayer is not uniform. But it's a very simple process, so the cost is very low. But the vertical one, this is very complex mechanical design. That's why its deposition or the epilayer is very uniform. So what we do here is like a dome shape, circular dome shape chamber. Within it, there is a pan, there is a plate. This plate is a circular, like a CD player, CD. So it's a circular, and on top of this plate, we place the wafer, which is substrate, and then the bottom of that wafer, I mean that disc or the plate, we have the heating system, RF heating. So when we send the gas through the gas inlet, and it goes up, and then because of the dome shape, it goes down, and then vertically it resides on top of the wafer, and the rest of the unused go out through the vent. So since the placement is done vertically, that's why here the deposition is uniform, but this is expensive because of complex nature of the system design. And the other one is between these two is called barrel type. Here many more wafer we can make deposition at a time. So it is like a upside down, it's a U shape, and then the barrel is like a kind of a cone, and it has different face, and each face can take wafer. We can place wafer in each face, so it is a batch process system. We can put a lot of wafer together in one process, and then the whole system is covered with this RF heating. This dotted ones are in the left, as well as it should be in the right, so it will be heating from outside, and the inlet gas come from the top, and then it goes in the bottom, get out from the vent, while it is inside, because of this temperature and then the environmental condition, so the gas react with the wafer, and then the epilayer deposited on top of each wafer. This one is not that bad like the horizontal one. Horizontal one is more tilted. Here it was tilted, it is not as much tilted like the horizontal one, but it is not as good as the vertical one. The vertical one, the deposition is straight, perpendicular on top of the surface. Here the surface is not on 100% perpendicular. Then we go look for the defects. So when you make the epilayer, we need to see what type of defects it causes. So if it is a plain crystal layer, then we don't have these defects. But if it is a layer, the shape is not plain. If you have a non-uniform structure, and we have to make a epilayer on top of it, then this shift in pattern may causes. Like if it is not the substrate, on top of the substrate, the material we want to make the epilayer, if it is not coming vertically, then what will happen? In one side, the epilayer will be thicker, and the other side the epilayer will be thinner. So as a result, where the center was, the center will be shifted. The center used to be here. Since this becomes thicker and this side become thinner, so the center moved from here to here. So what we usually do after creating this epilayer, we just, for the next process, we change the center. We change the center, alignment center, and then use the next process so that the center get aligned with the new center. So this is called shifting pattern. Another is called faceting or non-planarity. So this is happen when we have a selective epilayer growth. Selective. That means this hash area, these blocks are the resist. We don't want to make epilayer in these positions. And we want to make epilayer only between these two places. So this one is the wafer or the substrate, and on top of the substrate we will make a epilayer, but not everywhere, only selective positions. Here is one epilayer, here is another epilayer. So when we do this way, the top part of the epilayer becomes curved. It's not stay as a plane. So the middle part becomes more thicker than the corner part. তোমরা হয়তো দেখছো পারদ, পারদ যদি কোনো একটা প্লেটের মধ্যে রাখা হয়, ওটার যে বাবলটা তৈরি হয়, বাবলের উপরের অংশটা প্লেন থাকে না, কার্ভ থাকে। তো ওইরকমই এখানে যখন নাকি আমরা এপিলিয়ার তৈরি করি, it's get carved. So in this corner area is called faceting or non-planarity. So what we do to avoid these things? So we usually make the epilayer a little bit thicker than what we need, and then we etch out from the top to make it planar. So this is another defects for selective epilayer growth. So there are two types of defects we discussed over here. There are many other defects also. We are not going through those. And here is quality. We need to check the quality of the epilayer. So what we need to do, the quality depends on mobility, carrier concentration, doping profile, and thickness. Doping profile, as you remember, we did the doping profile for diffusion. The way we did in diffusion, we measured the doping profile for the epilayer also in the same way. It's called by measuring the shift resistance with 4-point probe method. If you go back to the diffusion chapter, you will find more details about it. This is the same method they use here, 4-point probe method, to find out the resistance. So if you get to know the resistance, then you can get the profile resistance or the sheet resistance. Sheet resistance depend on the doping profile. And second thing is like a thickness. Thickness, we also check thickness in diffusion. So we use two methods in there. One is the lapping, another is the grinding, if you remember, or if you check it in the diffusion. So here we don't use the grinding. Here we use the lapping process. Interferometer techniques we use to calculate the thickness of the epilayer. And for mobility and carrier concentration, we use make 4 sectors of the epilayer, and then we apply voltage and get the current, and from this we calculate using the Hall effect. Maybe in physics you have read those things. It's called Van der Poel techniques. Using that techniques, we can find out the mobility and carrier concentration for the epilier. So that's all for today regarding the epitaxy. So if you have any question, you can unmute your microphone and then you can ask me. Hello, anybody have any question? Pritam, do you have any question?
স্যার মোটামুটি বুঝছি স্যার, একটু পড়তে হবে নিজে, এখনো
Okay.
স্যার কোশ্চেন রাইজ হচ্ছে না।
Okay. Okay, so try to go through this material.
Yes, sir.
And I'll try to upload this recording also if it works out.
I have one question.
Sure.
এখানে সেলফ রেজিস্ট্যান্সটা কেন লাগতেছে?
হ্যাঁ,
সেলফ রেজিস্ট্যান্সটা কেন লাগতেছে, আর সেলফ রেজিস্ট্যান্সটা বের করার জন্য আমাদের কি ওয়েতে আগাইতে হবে?
shift resistance.
শিফট রেজিস্ট্যান্স।
Shift resistance it's called shift resistance because this resistance doesn't have much thickness. We have only length and width because these layers are so thin. So instead of saying it as a resistance, we call it sheet resistance. Sheet resistance is only the surface resistance. So if the surface resistance is according to our desire, then we can consider that the doping was properly done. And then how do you do that? We did explain in the 4-point probe method. So there are four point we keep on top of the wafer where we had the epilier. Then the two point supply the voltage, and then the current flows from the other 2 points. So and how much current will flow, it depends on the resistance on the sheet or resistance of this epilier. So from the applied voltage, how much current we get, we calculate the sheet resistance from there. So if you see the in the diffusion, we explain it that way, and the R equals to RS L by W. From there we can make RS equals to CV by L. So you will find it over there in the diffusion. I don't have that picture in here, otherwise I could have shown you. Okay.
ওকে স্যার।
Anybody else? Any more question? তো তোমরা এই জিনিসগুলো ভালো করে পড়ো। হ্যাঁ, এখনো আমরা ডিসাইড করি নাই how do you gonna take your final exam or the quizzes. So by the time probably we will find out a way, or maybe we will go by giving you assignments and then we assess those things. We haven't decided those things yet. So what you need to do, you just go through these things, and then you have any confusion, keep it to your mind, and when we will have a face-to-face class, we can discuss these things again. ঠিক আছে?
Yes sir. স্যার একটা অফ টপিক কোশ্চেন ছিল।
হ্যাঁ, শিওর।
স্যার আমরা স্যার এই যে ভার্সিটির একটা নোটিফিকেশনে দেখছিলাম মনে হয় যে থিসিসের ব্যাপারে আর কি, প্রতি উইকে একটা করে থিসিস ক্লাস হবে।
হ্যাঁ,
আপনার এখন স্যার আমরা তো স্যার আপনার আন্ডারে থিসিস করতেছি, এখন আমরা কি স্যার ক্লাস পাবো নাকি থিসিসটা আপাতত পজ থাকবে?
থিসিসের ব্যাপারে তুমি আমারে তোমার ইমেল সহ, তোমাদের সবার ইমেল সহ আমার একটা মেইল করো।
আচ্ছা স্যার, শিওর স্যার।
হ্যাঁ, তখন আমি এটা ওই আলাদাভাবে আলাপ করবো। ঠিক আছে?
জি স্যার।
ওকে। তো ভালো থাকো, আর নেক্সট ক্লাস এগেইন নেক্সট টিউজডেতে হবে 11:20। হ্যাঁ, আর তোমরা একটু অন্যদেরকে একটু অ্যাটেন্ড করতে বলো। উই নিড মোর স্টুডেন্ট। ওকে?
জি স্যার।
তো যার সাথে যার যোগাযোগ আছে একটু ওদেরকে নোটিফাই করো যাতে ক্লাসে আসে। হ্যাঁ,
শিওর স্যার।
Okay, thank you all.
Flowers.
আসসালামু আলাইকুম স্যার।